Welcome to Chapter 9, Section 7, Scale Drawings and Models. This is for Integrated Math 2 or IM2. I am reusing some of these videos, so sometimes the problems may not quite match up with the numbers, but they are in the correct order. So a couple things you're going to see on your screen here. The first thing you're going to see is a due date. I don't see that on the teacher's preview here, but you'll see it on your student screen. The second thing is the number of attempts. You always have unlimited attempts on tests, homework, and quizzes. Number of questions just tells you how many questions are on this assignment. Grading policy is best score, so whichever attempt is the best one is the one you keep. And partial credit is always enabled, so if you get 1 of 5 questions correct, you get credit for the 1 question, or however many you've answered correctly. Down here it says, please remember once you start the homework, you must finish it before you can work on anything else. What that means is once I click start, down here in the bottom right-hand corner, you will see a submit assignment button. I don't see that on the teacher preview here, but you will see it on your screen. And you want to click that button before you move away from the screen. So I don't mean like from problem to problem, before you close the screen, like clicking the little red X or closing your computer. You want to click the submit assignment button. Because number one, if you don't click the button, the system is going to lock you out of all of your other assignments, assuming you want to leave this attempt open. You have unlimited attempts. There's no reason to leave it open. Go ahead and click the button so that you're not locked out of topics or anything like that. It'll save your place. So as long as you have a little green check mark here, it'll save your progress. It just starts you up wherever you left off. The other big thing that this does is it affects the gradebook when you click a submit assignment. So your teacher can actually see what you've been working on. Before you click that button, your account is basically frozen. We don't get to see anything you've been working on. So good habit, always, always, always click that button. On the side here, we have explanation, example, and message center. So explanation tells you you're going to lose your question attempt because it's going to literally explain this problem. It's going to give you the answer. So it's not going to give you the answer and then let you come type it in. Sorry, not how this works. Example shows you an example of something similar to what we're looking at. I know it's a different figure, but same idea. We have a figure of a plane here. Here's a scale factor. It's going to ask us some questions about the scale factor, and we have to apply it. So we can close this. We can look at another example if we want to. We can also message our teacher directly from the screen. All right, let's go ahead and take a look at this section here. So we've been practicing what's called rigid transformations for the last 3 sections, which a rigid transformation, when we're talking about transformations in math, is how we move a figure around, we can say the screen, around a coordinate grid, so we can translate, meaning move it from right, left, up, or down. That's just a translation. We can rotate it or turn it, kind of like spinning it. We can also reflect it, and you can think of that as like looking in a mirror. It's a perfect image, but it's the opposite. It's a mirror image, so it's backwards. Those are all rigid transformations. What that means is it doesn't change the size or the shape of the object. It stays exactly the same size or shape. It just moves. Now with dilations, this isn't rigid anymore. With this, we're going to change the size of the shape. So with this one, we have a scale model of a table, and it's 1 centimeter represents 9 inches. So here's the scale model of a table. It's kind of like a little dollhouse table. It's a very teeny tiny table with 1 centimeter. And every centimeter on this little tiny table represents 9 inches in the real world or on the real table. So this is telling us this is the scale we're going to use. And it says down here in the scale model, the length of the table is 4 centimeters. What is the length of the real table? So I'm going to be, very silly here, and I have a table. I'm not very great with my artistry here, but we're going to pretend like I'm not drawing a very wonky looking table there. I'm not really sure what happened. I think that leg should go over there probably. Something like that. We're going to pretend like that's a nice looking table. So the length is 4 centimeters. 4 centimeters. So I have 1, 2, 3, 4. If I broke this up into 4 pieces. 1, 2, 3. Oh, I drew 4 lines. It would help if I were paying a little bit more attention. There we go. There's 4 pieces. 1, 2, 3, 4 pieces. Right? 4 centimeters. 1 centimeter each. Each centimeter represents 9 inches. So each one of these is actually 9 inches in the real world. So I could use something like this to convert these. I can say, oh, well, 9 times 3 or 9 times 4, that's going to get me 36 inches. Instead of 4 centimeters, it's 36. But instead of having to draw this out each time and actually divide it up this way, because it's not always easy to do it this way, what we can do is we can use this scale factor. So 1 centimeter to 9 inches like this, and that's going to equal, we want to make sure I have centimeters on the top, inches on the bottom. So 4 centimeters, and this is the model on the top. So here's the model, and then the real thing is going to be on the bottom. So I don't really know, and I'm going to change this. I just realized it's writing really tiny. I guess I can wait a second. So I don't know what the real one is, so I'm just going to use an X or whatever variable I feel like using. So now I'll go ahead and increase the size here. I had this zoomed in earlier, so that's why I made it smaller. It looks very like a pencil almost. So now I'm going to use cross products or cross multiplication. So 1 times x, I'm going to leave the centimeters and inches out. So I just have 1 times x, which is x, equals, and I'll use pink, I guess, for the other side, 4 times 9, which is 36. And this would have centimeters and inches, and this guy would have just centimeters, like that. So they would kind of cancel out. The centimeters would cancel out because there's centimeters on both sides. So they would go away. So I'm looking for just inches. But x was inches, right? We already knew it's on the bottom. It's going to have inches on it. So this is the idea of dimensional analysis, where we're carrying units through. But that can be a little confusing when we actually carry each unit through if we have multiple pieces to look at here. All right, so this is 36 inches. So down here it says the height of the real table is 18 inches. So now we have the height of the real table. And this is going to be a very bad drawing. It should be to this edge here, not to that other edge, but because that's more of a width. So I'll go like this. The height of the table is 18 inches. This is the real one. So I need to bring this back down to the model. It wants to know how big is the model. So let's use the scale factor again. We have 1 centimeter to 9 inches. That part doesn't change. That's going to be the scale throughout this whole problem. But now I don't know what the centimeters are. I do know what the inches are. It's 18 inches. Like this. So now I'm going to use cross multiplication. 1 times 18 gets me 18, and it would have centimeters and inches on it, but we're going to leave that off for now. And then I have 9 times x, which is just 9x. I want to solve for x because I want to know what is x. So I'm going to divide by 9 on both sides. And I'm going to have 18 divided by 9 is 2. So there are 2 9s and 8. We could also think of that. How many 9s are there here? There are 2 of them. So that would mean each one of these 9 inches is 1 centimeter on the table. So that's why it's 2 centimeters. So again, kind of a visual way to think about that, breaking it up, and the algebraic way with our cross products. All right. So let's get a new screen here so I don't have to rewrite all this. All right, so the table below gives the dimensions of a painting and a scale drawing of the painting. Find the scale factor of the drawing to the real painting. So this is important. We want the drawing to the real painting. So there was a drawing done and there's a real painting done. So this is kind of the model. This is the real thing. So make sure when you're doing this that you have the drawing figures or measurements on top and the real ones on the bottom. So pay attention to the way it says this to this. The first one goes on the top, the second one goes on the bottom. All right. So we want to just take a look at the scale for each one. We have length and we have width. So if we look at the length, we have drawing is 8 and the painting is 40. And we just want to reduce this. We don't want to turn it into a decimal. We just want to reduce it. It can divide by 8 on both top and bottom to reduce it. So we get 1 over 5. So this could be the scale factor. Every inch on the drawing is actually 5 inches on the real painting. So let's make sure that it's the same way for the width. So we have the drawing was 7 and the painting was 35. So both of these we want to reduce. Can divide by 7. So we get 1 over 5. So they do match. Perfect. That's what we wanted them to do. So that's definitely the way that works. Every inch on the drawing is actually 5 inches in real life. And sometimes scale, having a model of something makes it a lot easier to visualize it first before we go and make the real thing. So a lot of artists do this too, where they have sketches and drawings and they plan things out before they go and do this massive painting. Because if they didn't plan it out, it might not turn out exactly the way they had hoped, because they didn't put enough forethought into it. And a lot of things are like this. There's actually scale models that little kids play with. Hot Wheel cars, I don't think they're perfectly models to the real cars, but a lot of them are pretty darn close. They have opening and closing doors and the hoods open and close. They're little tiny models of cars. So the only problem with those is, like I said, I don't think they're necessarily perfect models. They're not exactly the same, but they do, function the same way. But a lot of big, even buildings before they're built, they make a scale model of it first so they can conceptualize it, they can see it before they go ahead and make the whole big building. All right, let's go ahead and get started here. So a scale drawing for a restaurant is shown below. All right, so we have a scale drawing. In the drawing, 2 centimeters represents 8 meters. Sorry, I don't know why I said 8. I saw 8 here and said 8 meters. 3 meters. Assuming the dining hall is rectangular, find the area of the real dining hall. All right, so we need to, number 1, kind of review what scale factor means. So remember, the drawing is smaller than the actual building, which makes sense. You wouldn't want to do a drawing the same size as the building. That wouldn't be terribly helpful. A scale model kind of helps us picture something before we build the entire thing. Or the layout when we put something together like this. So this drawing, is much smaller, obviously centimeters, than the actual kitchen and dining hall are going to be. But we know what the scale is. 2 centimeters represents 3 meters. So for every 2 centimeters on this diagram, it's 3 meters in the real world or in the real life. And we're assuming that it's rectangular and we want to find area. So we need to remember how to find area of a rectangle. So area of a rectangle, hopefully your rectangle looks more like a rectangle than mine, rectangle equals length times width. I mixed my D and my T together for some reason, which a lot of the time we just do L times W when we're saying length times width. So now we can go through and we can start looking at these pieces. So down below, if we want to know the area of just the dining hall, the kitchen is extra information, basically. We really don't need to know it, but they might have asked us a question about the kitchen or the dining hall. It didn't. It was kind of just by chance they asked us about the dining hall on this one. So they're giving you extra information. You don't need it. You just kind of ignore it. All I'm doing is going to focus on the dining hall here. So I know that the length of the dining hall, or the depth, I guess you could call it, I don't know, is 4 centimeters. And the width is 2 centimeters. So we want to go through and we want to start writing some ratios here. So let's see, we're going to find the length of the real dining hall and we're going to find the width of the real dining hall. So I kind of actually like to give myself a little map. So I do drawing to real and I set up a little proportion like this. So in the drawing, we have the length and then width. Is that what I want to do? Let's see. Oh, scale. That's what we're going to do. Sorry. Scale. And then length on this side. We'll do it that way. Mess myself up a little bit here on the video. So the scale for the drawing and for the real, they give us that up above. So 2 centimeters to 3 meters. So we have 2 centimeters. I said 2 and wrote 3. 2 centimeters to 3 meters. And then the length for the drawing, we have, I'm going to just go with 2. I guess I'll call that one length and this one width. I don't know. It doesn't really matter which one's which. So we'll go with 2 here for the drawing, and we don't know for the real. And we can do, length, we can do X, we can do whatever variable we would like to do there, just to represent that real quick. And then we're going to do cross multiplication because we have a fraction equaling a fraction, which is a proportion. So 2 times L is 2L equals 3 times 2, which is 6. So then I'm going to divide by 2 on both sides because I want to get L all by itself. 2 divided by 2 cancels. So the length of the real dining hall is 3, not centimeters. We just converted that to meters. And if we think about that too, every 2 centimeters represents 3 meters. Well, I had 2 centimeters. So that represents 3 meters. So that was kind of, hopefully a little bit more obvious conversion there. So you can also do that with the other one. You can say, well, there's 4 here, and every 2 represents 3 meters. So there's 2 and 2. That would be 3 and 3. So I can kind of figure this out without even doing the proportion. If I really kind of thought that through, I could divide each one of these up, because that's another visual way to do this, is if I have 2 centimeters and 4 centimeters, well, this guy, 2 is 3 meters. 4, I can divide that into 2 and 2 again, right? Because I want to break it into the 2's. So this is 3 meters and this is 3 meters. So I can break it up that way too, if that makes sense to you. It depends on the students if that visual representation makes sense. I know that doesn't always, sometimes the proportions don't always make sense to everybody. So we're going to do this again, drawing and real, scale, if I can spell scale, scale, and this time we're going to look at the width. All right, equals, okay. So 2/3, that's still the same scale. That's not going to change throughout the problem. But now the width is different. The width of the drawing is 4 centimeters. We don't know the width of the real dining hall. So I'm going to use W. All right, so now we'll go through and we'll go cross multiply. 2 times W is 2W. 3 times 4 is 12. I'm going to divide by 2, divide by 2. W equals 6. And it's going to be 6 meters, not 6 centimeters anymore. We needed to know this. Neither one of these are the answer, though. We need them to complete the answer. Remember, area is length times width. So we have 3 times 6, length times width, and that will give us, and I'm just going to keep it in red for whatever reason, 18 meters squared, because it was meters and meters. So meters times meters is meters squared. And this is an area, meaning it's 2-dimensional. It has length and width. If it's just meters, like 3 meters and 6 meters, that means it's a length. It's 1-dimensional. It's just one, it's a length or it's a width, but it's not both length and width. That's when we have squared on there. If we had cubed, now we're talking about 3-dimensional, which is volume. We're looking at the entire building. The length, the width, and the height of the building if we had cubed. So we're not looking at the volume right now, just the area.